Okay, so welcome to this first video on the Lebesgue integral. Okay, so the first thing to say is that the Lebesgue integral, the name can mean two things. Two very related things, but two different things. The Lebesgue integral can either refer to the general theory of integration that Henry Lebesgue developed. That's one definition, one usage of the word Lebesgue integral. It refers to this general theory of integration on an arbitrary measure space. That is not what we are going to study yet. We will come to that. We will come to the general theory of integration on an arbitrary measure space. But the other usage, and the more common, in my opinion, usage of the term the Lebesgue integral, is this abstract theory of integration defined on an arbitrary measure space, but where we're just studying it in the context of the real numbers. So our measure space is going to be defined on the real numbers. We're going to turn the real numbers into a measure space, and we're going to take this abstract definition of integration that works for any measure space and apply it to this setup on the real numbers, and that is what we are going to call the Lebesgue integral. And that's, I think, the more common. When people say the Lebesgue integral, they mean that, rather than the abstract theory of integration on an arbitrary measure space. The abstract theory of integration on an arbitrary measure space is extremely fascinating, and what it's similar to is you will learn the abstract theory of differentiation in the first course in analysis, and then maybe the second course in analysis you'll learn the theory of metric spaces, and you'll learn how to generalize the concept of the derivative to the metrical derivative, which can be defined on any abstract metric space rather than just the real line. Well, measure spaces are similar to that. They are the general concept, the axiomatic structure that you need to define a theory of integration, in the same way that a metric space is the abstract axiomatic structure you need to define a theory of differentiation. So you start to see how integration and differentiation actually start to pull apart. In the real numbers, they're completely and utterly intertwined with each other by the first and second fundamental theorem of calculus. But in the more abstract setting, they pull apart. Anyway, we're going to study the Lebesgue integral on the real line, and that's what we're going to call the Lebesgue integral. Okay, so this is going to require us to make the real numbers what is known as a measure space. And to do that, what we're going to have to do is we're going to have to define certain concepts. We're going to have to define what a measure is. We're going to have to define what a measure actually is acting on. But before that, I'm going to give you an example of a measure, the measure that we're going to work with, the measure that is on the real line. Okay, so firstly, I wanted to make a few definitions. So we are working with the real line. We are working with the real line with R. Okay, so firstly, a definition. This set, big curly I, like this, denotes the set containing all intervals. All intervals. So, for instance, any interval, for instance, of the form. What is an interval? I need to define for you what is an interval. Well, an interval is what is an interval? I don't know if I actually do know the rigorous definition of an interval. It's the intuitive picture is something like this. Here is an interval, A, B. So it has two endpoints, but it doesn't necessarily have to have an interval. So endpoints. So we have all intervals with endpoints. So IAB, and when I write IAB like this, it just means that I don't care really about the endpoints. I don't care whether you include the endpoint or not, or don't include the endpoint. So, for instance, all of these would be denoted IAB. So AB, the closed interval. Then we have the half open, half closed one. Well, there's the open one. Then we have the half open, half closed ones. Are both sides. So all of these would be denoted IAB. It's just any interval with the endpoints AB. but we don't care whether the endpoints are actually included in it or not. But all of those intervals would be in this set of intervals. So I'm not just having all open intervals, I'm having any interval you can think of. So all of those would be in there, where A and B are elements of the real numbers, but you would also have more elements in it than just those. You would also have things like A to... and again, I don't care whether it's closed here or open, it can be either of them, all the way up to infinity, so all the way up to plus infinity, so where A is any real number. And similarly, you would have minus infinity all the way down to A, and again, it can be open there or it can be closed. Both of those would be in this set. And then finally, the whole real line, which is minus infinity to infinity, that's an interval as well. So all of those sets, any set of those of that sort of form, is in this set. So this is a set of subsets of the real line. So we could say that I is a subset of the power set of the real line. And it obeys some very interesting properties, well, very nice properties. It obeys the properties called that when grouped together are given the name a semi-algebra of subsets. So I is a semi-algebra of subsets. And the axioms you have to obey to be a semi-algebra are firstly that the empty set has to be an element. So the empty set, for instance, just make the interval A to A. That does not include A, it doesn't include anything else. So that is the empty set. So the empty set is an interval. And the whole space is in there because this is the whole space. So that's an interval. So those two both will have to be in the I for it to be a semi-algebra. 2, if you have E1, or I should write I1, and I2, which are both elements of I, so if you take any two intervals, it has to be the case that I1 intersection I2 is also an element of the set of intervals. So that's another characterizing property. So obviously, it's intuitively obvious that if you take two intervals, either their intersection is empty, so you get the empty set, or their intersection is non-empty. So if you take, for instance, an arbitrary interval here and here, when you intersect them, you'll get another interval. I suppose to prove that property properly, what I'd have to do is make a rigorous definition of what an interval is. Well, I suppose if I just take... firstly, I could prove it for all ones where A and B are just elements of the real numbers. So we'll do this rigorously. So I, A, B, and then we'll take I, C, D. So either their intersection is empty, and all, by the way, all A, B, C, and D are elements of the real numbers, we're assuming for now, rather than looking at these intervals. We'll deal with them in a separate case. And basically, if it is empty, then either let's, without loss of generality, let's say that B is less than C. So it has to be the case that one of these is more this way than the other, basically. So we're saying basically that this one is on the left here, and this one is on the right. So it'll be the case that one is on the left and one is on the right. And if their intersection is not empty, then that must be the case that C is less than B, and then the interval CB is also an interval, and that's the intersection. That's not really a rigorous proof, but intuitively you can understand that the intersection of any two intervals is another interval. So it does obey that property, the set of all intervals. Thirdly, let's have another property. The final property is that if you take the complement of any interval, so you take all the things that are in the real numbers, which is defined to be the real numbers, subtract all the things that are in I1, then that isn't an interval. It's not necessarily an interval. For instance, if I just take the interval AB, then its complement is, well, it's this interval B to plus infinity, and you've also got this bit over here, which is A, negative infinity to A, like that. So it's the union of those, and that's the definition, that the complement has to be a disjoint union I is equal to 1 to n, a finite disjoint union of elements in the semi-algebra. So basically, you have the complement isn't necessarily in the set of intervals, but the complement is equal to the finite disjoint union of elements within the set of intervals. So those are the three axioms that you have to obey to be a semi-algebra, and the set of all intervals does obey those axioms. Now what we are going to do is define what is known as the length function, which is going to be our first example of a measure. So the length function is going to map, it's denoted lambda, the length function is what we're going to go on to next, the length function, and basically it maps all the elements in this set, the set of intervals, onto a length. It gives them all a length, 0 to plus infinity. So basically it attaches a size to this set of subsets of the real line, and that is the idea of a measure, that you take a set of subsets of the real line, or well, of any arbitrary set, but we're looking at the real line. So you take a set of subsets of the real line, and you define this function from that set of subsets onto the positive extended real numbers. Note that it can be plus infinity. And that attaches in some sense a size to the value, a size to that subset. So this is given by, it takes an interval IAB, and then that's why we denote IAB like this, because it does not matter whether it's got these points in or not, whether it's any one of these four up here. All that matters are the endpoints as far as the length function is concerned, and that's intuitive. We would say that the length for all these intervals is exactly the same. So the length function takes an interval IAB and it maps it onto it maps it either onto b minus a if a and b are both elements of the real numbers, and it maps it onto plus infinity if b is equal to plus infinity, or a is equal to minus infinity, or b is equal to plus infinity and a is equal to minus infinity. So any interval which goes off to infinity is given the length plus infinity. So that is the length function, which maps this set of intervals onto a length, so size. Okay. And it obeys some axioms. A measure needs to obey some axioms. This function is a measure. And the axioms it has to obey to be a measure are: 1, firstly, that the length of the empty set has to equal 0. That is true because the empty set could be denoted A, and then if we take the length of that, it's going to be A minus A, which is 0. So that's true. 2, that if you take the length of a union, of a disjoint union, I is equal to 1 to infinity, and it can be countably infinite union of I is equal to the sum I is equal to 1 to infinity length of I. And that's an intuitive property because if you take, for instance, all we're saying basically is take an interval, well, I'll draw a new picture down here. Take an interval, let's call this AB, split it up into an infinite number of pieces. So this interval is the union of these infinite number of pieces, and they're going to go on and on. Then the length of the overall interval is the sum of all of these individual pieces. Now the condition for that to hold is that each of these pieces is disjoint. Of course, we're not going to get everything if we're not careful. We need to make sure that some of these are half open and half closed so that they all stack up overall to give you what you want. Basically, all the intervals have to be disjoint, meaning that their intersection is empty, and that's what this square union means, that you're unioning disjoint sets. We could write that I intersection ij is equal to the empty set for I is not equal to j, i.e. that their intersection is empty, meaning that they are disjoint if they're not the same interval. Then the length of the overall union that they make is equal to the sum. Well, it's going to be a sum if it's only a finite union. So if it's a finite union, then this will become n up here, and the length of the union will just be the sum of the lengths of the constituent pieces. However, obviously, if you're unioning in a countable infinite number, then instead what you have to take is the limit of these partial sums. So the limit of the partial sum, so you'd add up a certain number and you'd take the limit of the sequence as you add more and more and more. Okay, so that is the definition. This property here is called countable additivity. And again, it's intuitively obvious that this length, well, it's not obvious, but intuitively we would think that this length function defined on the intervals is going to obey those properties, and indeed it does. In the next video, what I'm going to do is show you the concept of the Lebesgue outer measure, which is a way of extending the length function, because what we'd like to do is we'd like to be able to take the length of sets which aren't intervals. So for instance, one of the main motivations for why the Riemann integral was a problem was that if you take the function which maps all rationals onto 1 and all non-rationals onto 0, the indicator function for the rationals, then that has no Riemann integral. What we would like is for the integral to be 0. So what we'd like to be able to do is we would like to be able to measure, we'd like to be able to attach a length to the set of all rationals. The set of all rationals is not an interval, so we can't do it just with this. What we'd like to be able to do is extend the length function onto a bigger subset of the power set of the real line. In fact, what we're going to do, the Lebesgue outer measure is a way of extending it onto any subset of the real line. The problem is that it no longer is a measure, which is why it's called an outer measure. It does not obey this property here, this second one. Countable additivity fails. So what we will then do is we will say, well, what is the biggest subset of the power set of the real line for which this Lebesgue outer measure, if we just restrict it to those sets, it is countably additive, and that will lead us to the Lebesgue measurable sets of the real numbers. And then what we will do is we will say that if you have a function that can be written in terms of I'll save that for later. If you have a function that in a sense the inverse images of if you take basically, if you this is going to be very, very important, because the only time we're going to be able to integrate any function where the pre-image of any value in the codomain, if that is a Lebesgue measurable set, then we can attach a value to the size of that, and then we'll be able to define a better notion of integration, basically.